Hey all, so in this problem we want to figure out the force that this woman can push on this crate of 4 boxes to prevent them from either slipping backwards towards her as she accelerates the cart to the right, or if the coefficient of friction is large enough to prevent them from toppling over in the counterclockwise direction. So let's start by doing a torque balance, and let's assume that the coefficient of friction is large enough when she pushes on it. The coefficient of friction is large enough when they would topple overward that they wouldn't slide relative to the cart. So let's begin with a free body diagram, in which at the center of gravity we've got some weight acting downward, and we can call this point A, and there's a normal force acting upward at point A, and a force of friction acting to the right. And I'm drawing the free body diagram right at the point that these boxes would topple over. So in essence, all of the weight would be accumulated at point A. And this is right when they're teetering on toppling backwards towards her. So this is the maximum acceleration she could push, the maximum force in this direction, maximum frictional force. So normal force acting upward, and then a force of friction acting from left to right. I want to use an equation that you may not have used much, but that is, it's saying that the sum of moments, let's do a torque balance, a moment balance around point A. The sum of moments will equal the sum of the kinetic moments around point A. So this is that scripted M again. So what's going to happen is that there's some frictional force, and it's acting down, looks like 1.5 feet plus 1.5 feet, or 3 feet down below the center of gravity. So this frictional force acting down here will result in, it would result in a counterclockwise rotation if it was large enough. And we're going to figure out right at the point where they begin to topple. So I want to show you how to use this equation, and I chose point A. Let's do it around point A because it knocks out the normal force, this normal force at point A, and it knocks out the force of friction simply because the distance between, well, simply because the point is centered at these two forces. So in our moment balance, we'll knock off both of those. So the sum of moments about this we'll say 1 foot from point A. It's 1 foot over. The boxes are 2 feet wide, so the weight, the gravitational force, the weight, mg is acting 1 foot to the right of point A. And this moment is acting in the clockwise direction, so we'll leave a positive sign in front of that. And that's about point A. That is the only moment acting on point A. So we've just got one moment. So we've dealt with this side. We've dealt with the sum of moments. And let's look at the sum of kinetic moments. So when you apply this equation, the sum of the kinetic moments, first thing is to draw a kinetic diagram. And the kinetic diagram will draw the center of mass, point G, and it's accelerating to the right, max. And there is no vertical acceleration, there is no angular acceleration in this case. The boxes, they're only accelerating from left to right. So draw this in the kinetic diagram, draw any accelerations at the center of mass, any vertical or horizontal directions of any moving part, and then draw whether it's rotating clockwise or counterclockwise. In the solutions manual and throughout the book in examples, what you'll see is that they'll use this equality symbol, and they'll say the free body diagram, the forces and the torques, the moments acting on this free body diagram we'll equate them to all of the accelerations or the kinetic moments in the kinetic diagram. So this equality right here is effectively the equality sum of moments equaling the sum of kinetic moments. So when we draw this, what do we got? We've got a vertical distance of 3 feet acting upward. And in the kinetic diagram, you can treat these, you can look at them, you can almost visualize them as being forces, but these kinetic moments, you'll apply it just like a torque balance. And so we've got around point A, we've got max, it's acting 3 feet above point A. So we can draw it as mka. So the sum of kinetic moments is equal to 3 feet times max. And again, it's acting, this kinetic moment's acting in the clockwise direction, so we leave the positive sign. So if we apply this equality, we've got the sum of moments, we've now got the sum of kinetic moments. So let's set this equal. We've got 1 foot mg is equal to 3 feet max, and the masses will cancel. And we can now solve. So let's figure out what the acceleration would cause the boxes to topple over. So solving for AX in this case, we've got 32.2 foot per second squared multiplied by a third effectively, and we'll come up with an acceleration in the x direction of about 11 feet per second squared, 10.7 feet per second squared. Any acceleration greater than this would cause the boxes to topple over counterclockwise. Anything less than this, and they'll stay upright. So right at this point, they're right on the brink of toppling over backwards. So we'll do sum of forces in the x direction's got to equal max. And what we want to figure out is to verify if the force of friction is sufficient enough to cause an acceleration of 10.7 feet per second squared. If it's not, if you can imagine a coefficient of friction that was real small, if this cart was real slippery, all would happen, she would accelerate it to the right, and the boxes would effectively slip backwards towards her. They wouldn't topple over because there isn't enough torque to cause them to fall over, but they will slip on the plate. So what we've assumed right now is that they'll stick relative to the flat surface of the cart. So we'll figure that out in a sec. But anyway, let's figure out, we've got the sum of forces got to equal the mass times the acceleration in the x direction. So the force of friction, coefficient of friction times its weight will equal max. There's only one force acting in the horizontal direction. So we'll knock off, the m's will go away, and we can solve, in this case, for ax. And what this will tell us is the acceleration she'd have to apply to cause the boxes to slip. So this is dependent on the coefficient of friction. And what we come up with is a value of 16.1 feet per second squared. So this is the acceleration that would be needed to make the boxes slip. We've already determined that the boxes would topple over at an acceleration of 10.7 feet per second squared. So what we can conclude from this is that the boxes, they're not going to slip at the acceleration in which they would topple over, because that acceleration would be smaller than the acceleration needed to make them slip. So here it is in words: because the acceleration needed to make them topple over is less than the acceleration needed to make them slip, consequently the boxes would topple over instead of slipping at this point. So we'll determine, to wrap things up, we'll determine the maximum force. It's acting at a 30-degree angle. So sum of forces, and I'm doing a force balance around, I guess, the boxes and the cart right now. So we'll say, we'll have to figure out the mass of the boxes and the mass of the cart. But we know the maximum acceleration they could have is 10.7 feet per second. So sum of forces equals max. We've got ax is equal a maximum of 10.7 feet per second squared. So the mass of everything, we've got 4 boxes. Each box weighs 8 pounds apiece, and then we've got the 30-pound cart. So divide that by the conversion factor. Each one slug weighs 32.2 pounds. So we come up with a mass of 1.93 slugs. So rearrange it, solve for the force. We come up with 1.9 slugs times the acceleration divided by the cosine 30, and we come up with a final value of 23.9. It'll be 23.9 slug foot per second squared. And a slug foot per second squared is the same thing as a kilogram meter per second squared. So you'd quickly convert that to newtons. But just like that, so we can quickly convert this to pounds. So final answer of just shy of 24 pounds. Anything more than that, the boxes would topple over.